Hey everybody, I hope you tuned in to Microbiology Twitter Journal Club last week. We had a great conversation about how researchers added new letters to the genetic alphabet. A big thanks should go out to all the people who joined in, and if you didn't make this one, don't worry, I'm going to run through some of the discussion here. First, come the criticisms. Sometimes when I read papers, I get starstruck. I just find that everything fits together in just the way I like it, and it all feels right. I've learned over the years not to trust this emotion, and that more often than not, it means I just haven't read the paper closely enough, or I'm completely out of my depth, which is why Microbiology Twitter Journal Club is quite useful. Twitter user Heath O'Brien brought the skeptical, pointing out an irregularity in one of the figures. In the paper, the authors noticed that overexpressing nucleotide triphosphate transporters slowed down the growth of bacteria. They say that actually, when they include their unnatural bases, this somehow improves the growth of bacteria, that it overrides whatever it is about the nucleotide triphosphate transporters that makes them lethal to the cells. So let's go straight to figure 2b. You have to think about what does it show? Where is the effect? So no, the grey dots are the cells with just nothing in them, normal cells, and look at them, they grow terribly. If you add the plasmid, the cells start growing a lot better. If you add the base pairs to cells that already have the plasmid, there isn't much difference in the growth. So the figure doesn't quite match what they're saying in the text. But wait, they did show some data in their supplementary section, in a table that describes just one growth experiment looking at 2 time points, and actually only just one of those time points backs them up. So in real terms, there doesn't seem to be much difference. You could speculate on there being a growth flag based on this, but cell cultures can vary a lot in their growth. That's why you need statistics to work out whether a difference actually means anything in real terms. The authors are presenting contradictory evidence. It could be that the figure labels got mixed up on that one graph, but I can't give them a free pass for that. So now let's talk about future work. Quite a lot of people were actually really excited about the prospects for this paper. If anything, the researchers didn't go quite far enough. Sure, they put in the bases, but they didn't do anything with them. That would be the next step, so the question is, what would they be used for? Perhaps they could be used to identify and differentiate synthetic organisms from natural organisms, sort of like a genetic tag. DF49219398 pointed out that these could be used to code for alien amino acids. What does this mean, you may ask? Well, you see, all the living things that we know of use 24 amino acids, but there are a whole lot more amino acids out there. At least 40 unnatural amino acids have been artificially incorporated into proteins. If you use these unnatural base pairs in an expanded genetic code, you can now code for all these new amino acids and incorporate them into the kinds of proteins that we'd never see in the natural world. And of course, now we should go to the limitations of the study, because there are some limitations of the work that will for the moment keep all that future work in the realm of dreams. For a start, the researchers need to find a way for cells to synthesize unnatural base pairs. This way they don't need to keep adding the bases to the medium, and they no longer need to bother with those troublesome nucleotide transporters. The second limitation is that even if they did put in these synthetic pathways, they are already limited because you can only put the unnatural base pairs in using DNA polymerase 1, which, as I talked about in my previous video, only acts on a small amount of the genome. But that can be overcome through mutating DNA polymerase 2 and evolving it so that it accepts the unnatural base pairs. But the biggest hurdle, the one that could be a giant game over to this entire enterprise, is the fact that these bases only work because they cannot form hydrogen bonds. Allow me to explain. DNA strands themselves are held together using hydrogen bonds. If you have too many of these unnatural base pairs on the DNA strand, theoretically, it could make it quite unstable. You probably can't have long repeats of hydrophobic bases, so these DNA strands would flop around and become more vulnerable to breaking. The paper isn't perfect, but very few papers are. But just because there are bad parts doesn't detract from its good parts. They haven't pinned down the effects of unnatural base pairs on cell growth. That was never the focus of the paper. They wanted to create a cell that uses unnatural bases, and for that at least, they've provided enough evidence to back that assertion up.